Swayam Prabha. Digital India. Educated India.
So, in the last class we have started discussion on free vibration of damped single degree freedom system. We have seen that depending on the system damping, it can have either an aperiodic motion or a periodic motion. So, when the damping is above a critical value, then the system performs non-oscillatory aperiodic motion if the system is disturbed from its equilibrium position. On the other hand, when the damping is lower than the critical damping for that particular system, then the system executes oscillatory motion, but not with constant amplitude, it decreases exponentially. What we will do today, we will continue our discussion on the single degree freedom systems with damping and investigate little bit more of the kind of or the nature of motions of such systems with the damping more than the critical and damping at the critical level. We would also like to find out ways and means to find out the critical value of damping coefficient for a particular given system. This is the system we have been studying and we continue our discussion on that. So, when we also know that we have found out the ratio of the damping coefficient and the critical value of the damping coefficient can be written as a non-dimensional quantity which is called the damping factor. When zeta more than equal to 1, it leads to aperiodic motion. We will investigate little bit more about the motion of such systems when zeta is equal to or more than 1. The general solution for x can be written like this. Where A and B are to be determined from the initial conditions. Let us give the initial conditions like this. X is equal to x0 and x dot equal to x dot. Once these two quantities are given, the subsequent motion will be completely known. This is x, then x dot will be Now, when we put these conditions, let us say that x is equal to x0 at t is equal to 0. So, t is equal to 0 means this will be equal to 1, this will be equal to 1, or x0 equal to a into 1 plus b. Similarly, when we put this condition, that is at t is equal to 0, again this is 1 and this is 1, and what remains is equal to x dot 0. So, we have two equations with two unknowns a and b. So, a and b, this is a set of simultaneous equations, and we can solve. Instead of wasting time in determining this in a long way, I will just give the results. And obviously, the solution can be written by using a and b, substituting the values of a and b here. I am not writing it because it will take a lot of space. Now, of course, you can see here both these terms in xt. So, this one is a quantity which is negative real number, because this is less than zeta but positive, this is minus zeta. So, therefore, this quantity will be negative and this term will be decaying with time, as I mentioned earlier. Same is the case here. This is less than 1, but both being negative, it is obviously a larger negative value than this, and this will also decay exponentially. So, therefore, we can get that this system will asymptotically decay. The question is, so as minus z plus zeta square minus 1 and minus zeta minus 1 are negative real quantities, this is fine. Now, our question is, when it decays, when t tends to infinity, now it will decay like this or it will decay like this. That is something which is of interest. That means whether there is any value of t, any real positive value of t for which xt is 0. So therefore, the question is that for this value of t, xt is equal to. So let us find out if and when such a thing is possible. Now, if xt is 0, that means what we get? If xt is 0, then obviously this means that a e to the power minus zeta plus zeta square minus 1 omega n t is equal to minus So, if we can find out a positive real value of t from this condition, that is the value where xt can be 0, means that the mass will cross the equilibrium position. So, I think if we now try to see that first of all e to the power minus zeta omega and t, e to the power minus zeta omega and t will cancel from both sides. So, this will give us e to the power 2 equal to minus b by a. Because I take this e to the power minus this, when you bring it to this side it becomes e to the power plus, and so this becomes y minus b by a, or which is nothing but so one thing, this condition is satisfied for two values of t. One, when t tends to infinity, then this is 0 and this is also 0, the condition is satisfied. The other value of t for which it will be satisfied will have to be found out from this. Now, rather than solving for t, let us find out the conditions under which a real positive value of t is possible. Now, if since this quantity is positive, omega n is positive, so t is also positive. So therefore, if t is positive real quantity, then e to the power this thing will have to be a quantity which is more than 1. So therefore, this for what, under what condition this will be greater than 1, that will give us a real positive value of t. That means a crossing the equilibrium position will be possible. So let us find out that. Now, first of all, when zeta is greater than 1, obviously the whole thing we are doing. Now, if x dot 0 and x 0 are of same sign. What happens? If they are either both positive or both negative, then what happens? If they are both positive, then it is as such. And you can see that this quantity is definitely smaller than this quantity. So as a whole, the numerator is smaller than the denominator, and this whole quantity is less than 1. If we consider that this is equal to, say, some quantity, say gamma, capital, then capital gamma is less than 1. And so no positive real value for t is possible, or it will never cross the equilibrium line. Basically, it means that. Now, next thing, suppose if x dot 0 and x 0 are of opposite sign. Then what happens? Now you will find that if suppose x dot 0 is positive and x 0 is negative. So this is positive, then this is negative, means this will be x dot 0 minus a negative, actually plus a negative quantity means minus this quantity, and this is positive and this is again negative, so this will be. So you will find that as such there cannot be any decision that whether gamma will be less than 1 or more than 1. But there is a further condition that if or and magnitude of then what happens? So that means magnitude of this is more than magnitude of this. Then if this is positive and this is negative, now if magnitude of this is anyway a smaller quantity than this, so this will be a positive quantity minus some quantity which is less than this. So what will happen? The upper part, and this magnitude of x0 is more than this. That means when this is negative sign is put, in the bottom you will get a positive quantity. Here, of course, again, since x dot 0 is more than this in magnitude, x dot 0 will be more than this also in magnitude, because this is smaller than this. So what we are getting, that it will be x dot 0 minus a quantity, and below x dot 0 minus a quantity which is larger than this. So what will happen? The numerator will be a positive quantity, but and numerator will be a positive quantity, denominator also will be a positive quantity, but this will be less than in magnitude. So that means gamma will be more than 1. If x dot 0 is positive, x 0 is negative. Now if it is the other way around, if x dot 0 is negative and x 0 is positive, then we can take minus common here, this cancels, so ultimately we get again the same thing. So therefore, if x dot 0 and x 0 are of opposite signs and x dot 0 is of sufficient magnitude to be larger than this quantity in magnitude, then only there will be possibility of 0 crossing like this. So this is for the case when x dot 0 is, that means actually it should have been like this. So similarly, here if you have x dot 0 is negative, but you have to give a positive velocity, then again you will find. But if you give a lesser velocity, we go like this. So you have to give sufficient high velocity so that it crosses, and that condition is obtained from this. So for overdamped situation, the motion will be always aperiodic, and the possibility is that it may cross the equilibrium position only once, and that too again the condition is that the initial velocity and initial position should be of opposite sign, and initial velocity should be of enough magnitude to be more than this quantity. That is when it is possible for the mass block to cross the equilibrium position. Now if the system is critically damped, general solution in this case we have already seen will be e to the power. Now zeta is equal to 1, so it will be simply, actually zeta is here but zeta is 1, and initial condition are as before x0 and x dot 0 as t is equal to 0. So simply here we can write that x dot t is equal to minus omega n a e to the power minus omega n t plus b e to the power omega n t minus omega n dt by differentiating this quantity with respect to time once. Now if you put the initial conditions that x0 is equal to a, when you put t is equal to 0, this becomes 1 and this becomes 0, so simply this. And x dot 0, when you put t is equal to 0 here, this term goes, this becomes b, this becomes, so it will be b minus so these two equations can be solved very easily to give the final value, and the general solution becomes of the form A is this, and so we find that as t increases, now this is an exponentially decaying term, so finally, so even this term is increasing with t, but this is increasing linearly and this is decreasing exponentially, so eventually it will also decay exponentially, just like the case where we have overdamped situation. Only thing here we know that it will return to the equilibrium position at the quickest possible time. Here also let us find out that whether it can cross the equilibrium position. That means whether x can be 0. Now, here xt will be 0 means two conditions, when t tends to infinity, or as before there will be another situation when this is equal to 0. This is equal to 0 means t is equal to this. So again t to be positive, x0 and x dot 0 must be of opposite sign. And that is not enough as before. That means the velocity has to be sufficiently large and magnitude of the velocity has to be more than magnitude of. So here the case is simplified little bit, but the basic logic is the same, that when they are of same sign, that be both positive or both negative, you will find that this is going not never possible to make it a real positive number. If they are opposite, then it is possible that, and x dot 0 is more than this in quantity, you can easily show that t will be positive real. So in that case it will cross the equilibrium position only once, because t can have only two values. Once t is equal to infinity, other is particular value obtained by this. Now the next question is to investigate the critical damping in more details. It is fine that in this kind of a system the critical damping is given however, the mechanical system may not be always of this form. It can be of different configurations. So how to find out the value of the coefficient which corresponds to the critical condition, we should be able to find it out. So, let us now take up the task of finding the critical damping coefficient for system. Now, here it is the system which we have already done, and you know the differential equation for this is mx2 dot plus cx dot plus kx equal to 0, and we know that the characteristic equation will be ms square cs plus k, and obviously the critical damping coefficient is obtained by now. In this case, what is going to be the equation of motion? Now, you will find that the system is a pure rotary motion. So, therefore, let us consider only torque. What are the torques acting? The spring torque, suppose if it is going in this direction, so the spring moment will be capital K into theta, and if it is rotating in this direction with a velocity theta dot, then what will be the velocity here? The radius at which this damper has been placed is r. So, linear velocity of the dashpot piston will be r into theta dot. So, the damping force will be C into r into theta dot, and its torque here again will be r square into theta dot into C. So, again there will be resisting torque, it will be C r square theta. That means the force generated is velocity here, that is r into theta dot into C, and the torque of or moment of that force here, because you are writing only a moment equation, it will be multiplied by this arm, and that is again r, which therefore makes it this. So, the equation of motion we get is I theta 2 dot in this direction is equal to minus this plus or minus this. That means, if you bring to one side, now assuming the solution in the same usual form like e to the power st, the characteristic equation will be E I s square plus C r square s plus k equal to 0, and so S1 and 2 will be and this gives us that critical value means this has to be 0, and so Cc becomes equal to 2 square root of I k divided by the last case. Again, it is an angular motion. The forces are, one is weight, and when it is moving theta dot, its velocity of the piston is b into theta dot. So, force will be c into b into theta dot, and its moment here will be c into b into theta dot into b. So, therefore, b square theta dot into. Now, so the moment of the damping force is given by this. What will be the moment of the restoration force? It will be moment of this force. If the length here is L, this is L into sine theta, as this angle is theta. But we always remember this thing, we always consider small oscillation. So, this is approximately equal to L into theta, sin theta is theta, otherwise you will have a nonlinear equation. So, therefore, the moment of inertia of this is m L square into theta 2 dot plus C b square theta dot plus mg L theta is equal to 0, and obviously ml square s square plus cb square s plus mg L equal to 0 is the characteristic equation. The two roots will be these are the two roots, and obviously the critical value of C will be that for which this will be 0. So, these are the simple cases where the critical damping coefficient expression will depend on the system. So, we will take up now a proper example to solve. So, the system is like this: a massless rigid rod hinged at O is approximately horizontal position and carries a mass, concentrated mass m. At a distance from the hinge A, a spring is attached of stiffness K. At a distance B from the hinge, a viscous dashpot of damping coefficient C is attached, and the system of course is in equilibrium under gravity. Now, if we displace it from this equilibrium position, what will be the critical value of the damping coefficient C, so that it just stops oscillating, it executes aperiodic motion. So, here again we should remember the cardinal principle. We have proved that since the system is in equilibrium under gravity and we measure the displacement of the configuration from that position, we forget about gravity and we measure the displacements everything from the equilibrium position itself. So, the free body diagram if it now suppose we consider that it undergoes a displacement theta from the equilibrium position. So, how much is the stretch here? It will be A into theta for small theta. So, the spring force will be A theta. Similarly, what will be the velocity of this point? B into theta dot, and the force acting here will be C into B theta. So, the equation of motion we can now write about point O, ml square theta 2 dot will be equal to total moment in that direction, which will be minus this into A minus this into B. So, therefore, if we bring it to the same side, we will get plus CB square theta dot and plus A square theta. Because when you take moment about this point, you have to multiply this by A. When you take the moment about this point, you have to multiply this by B. So, our characteristic equation will be so two values will be and obviously the critical value of damping coefficient C will be such that this is 0. So, Cc is equal to so therefore, we have to keep this in mind that for each and every individual configuration or a system, there exists a different expression for the damping coefficient. So, you should never consider the damping coefficient's critical value is always given by this. Each time it has to be found out. So, far as the application of the critical damping coefficient we have already mentioned, that I think you understand that the practical applications will be all in such cases, all such cases where you do not want the system to cross the equilibrium position or rather approach the equilibrium position with negligible velocity. So, now to sum up the matter concerning viscously damped single degree freedom system free vibration problem, we have seen that cases can be underdamped, and in underdamped situation the oscillation of the system decays like this. If the system is critically damped, then the system can behave like this, that if you push it like this, it will go like this. If you just leave it here, it will go like this, and if you push it down hard enough, it will go like this. Finally, in case of over damped situation cases. If you push it hard, it will go like this. If you leave it like this, it will go like this. And if you push hard enough, so the characteristics of the under damped or critically damped and over damped, they look similar. Only thing we find that the decay is slower, or the approach time for the equilibrium position is always longer in case of over damped system. The characteristics being same, here the only difference that it approaches the equilibrium position in the quickest possible time. In case of under damped system, it, as mentioned, that it decays exponentially, and this decay is measured by quantity called logarithmic decrement. That is the definition, and value of delta is equal to is approximately equal to 2 pi zeta when zeta is very small. So this is a measure of the decay rate, and we have also seen that decay in viscously damped system can be also indicated by the amount of energy dissipated per cycle divided by the maximum energy in the cycle, and that is also related to delta and those derivations we have seen. So this is in a nutshell about the viscously damped single degree freedom system and their vibration characteristics. Next, I think we have to take up the case of the system where we have solid friction, that means Coulomb damping, and in the next lecture we propose to take up the single degree freedom system with Coulomb damping, its free vibration.